Adrian Muscat, which is the pilot lead researchers for the Malta case. He holds a professorship at the Department of Communication and Computer Engineering at University of Malta, and he is head of the R&D at Green Roads Ltd.
Hello, Elisabetta. Thanks for the introduction. So yeah, I will be presenting the case of the smart city test case in Malta. So these test cases are based on societal challenges that arise from mobility. So we will be looking at that mobility contributes significant to land use, public space taken up by the roads, and it leads to premature deaths and injuries, unfortunately, and pollution and congestion, which the latter two have got lead to increased health problems, lowering of quality of life, and an effect on climate change. It is therefore desired to have efficient land use, increased safety, and lesser pollution. And the pilot that we are running in Malta will be showcasing technology that can help in the management and planning of urban mobility. We are looking at two aspects here on how to tackle these problems. One of them is encouraging sustainable mobility, especially commuting by bicycle, which in the island of Malta, it is practically at its infancy. And we are trying to address this by increasing safety for cyclists and data-driven insights for efficient and safer infrastructure, and identify areas for enforcement and/or education campaigns. The other aspect is monitoring the use and allocation of the transport resources, such as that can lead to minimizing the additional land use, reduction of vehicle emissions, for example, by tackling congestion, and timely maintenance of physical infrastructure. The use cases will showcase data analytics tech that can address some of the above items, maybe not all of them. Green Roads is a technology startup and is essentially focused on developing technology that can be used to tackle problems with respect to urban mobility. And essentially the core product of Green Roads is a set of AI models to analyze video traffic data, which is then further processed and visualized on cloud infrastructure dashboard. The idea of these models is that there are a potential number of uses, such as, for example, data-driven long-term decision-making, managing road space, and so on. And the Project Marvel is very important for Green Roads because it gives us exposure and building connections in these areas of data analytics. And not only that, but it also it has got shared goals, and we gain added know-how. And we have the opportunity to experiment with novel products as well. So essentially, this has been mentioned by previous speakers. This is about transforming existing city passive sensors, typically manually monitored in control rooms, recorded or live, into transforming this into useful data insights. It has to be GDPR compliant and anonymous outputs to process as needed and preserves privacy. And Project Marvel is well into that as well. And it introduces us also into multimodal data with the introduction of audio, processed over heterogeneous infrastructure. And there is also the aspect of data, exportable data, and easier integration and management of data. Now, with regards to our contribution in Project Marvel, this picture depicts the infrastructure and models that we will be using. Essentially, in the sensing elements, we've got CCTV audio-video cameras. We're also allowing space for third-party cameras, such that anybody interested in these use cases can perhaps contribute as well. And we are also developing some prototypes for running the experiments, such as the Green Edge audio-video sensor, which uses the IFAG audio hub nano with 2 microphones, Raspberry Pi camera, and other microphones. At the edge, we are planning to compute on Raspberry Pis, CPUs and GPUs, specifically for embedded systems, to execute, for example, sound event detection at the edge, our own video analytics software, security at the edge, and anonymization and anomaly detection models at the edge. The idea here is to, of course, reduce the data flow volume. We're also computing at the fog layer on the Green Roads infrastructure, and which is made up of CPUs and GPU. And we will be running inference AI models there and data anonymization if it's not completely executed at the edge. And then the data moves onto the cloud. So it pretty much follows, of course, the Marvel edge to fog to cloud infrastructure. And now I will go through 4 use cases that we will be implementing here in Malta. So the first use case is on safer roads for bicycle commuting. And this is motivated by the need to encourage and facilitate cycling, thereby reducing car dependency and its negative effects. This is part of the Malta National Transport Strategy, which looks up at the strategy up till 2050. And so how can we facilitate cycling or encourage cycling? Local research studies strongly indicate 2 main obstacles to cycling: the perceived lack of safety on the road and the lack of dedicated cycling infrastructure. This is from research carried out at the University of Malta by Mas and Attard. And this is some further background on why this use case is very relevant in Malta. So over the last years, efforts from both the authorities and the cycling community lobby were in encouraging cycling, mainly through infrastructural changes. Essentially, we saw the introduction of some segregated cycle paths, like this diagram on the right here, where the cyclists are separate from the cars, and also shared infrastructures, like the picture here shown on the left. In this case, the inner carriageway is shared between vehicles and cyclists, obviously due to lack of more land or physical space. And in particular, this case, prior to changing the road into dual carriageway, there was actually a segregated cycle lane here. As soon as this was converted to a shared lane, that discouraged cyclists. And it is also more important here for the drivers to pay attention. So this use case is tackling this situation of making these shared lanes safer for the cyclists. Essentially, it's about developing technology that assists vehicle drivers when cyclists are present on the road. So in summary, this use case would run as follows. So we would detect cyclists using cyclist detectors, or bicycle detectors rather than cyclists, exiting a junction, and inform car drivers of the presence of cyclists via either variable message signs or equivalent, such as these red triangles here. This is basically be aware of cyclist information system. And hopefully cars would pay more attention and reduce the speed. In such situations, cars have to reduce the speed below the signposted speed limit. This is the main problem here. Technologically, there are some challenges here. First of all, it has to run in real time, very low latency. So it has to operate at the edge, which brings more problems. The AI model is at the edge, and that means we have to use GPUs there. One problem is detection in low visibility conditions, which is when we actually want to detect cyclists even more. The picture here on the right shows a cyclist at night and during rain as well. It was raining. Obviously, cyclists who don't use high visibility clothing won't help the cameras to detect them. And we also have a problem with the computer vision system that sometimes bicycles are confused with motorcycles. So in this case, it might be good to fuse audio and video together. The second use case is on studying road user behavior. And the motivation is coming from the fact that Malta has experienced fast changes in the transport physical landscape, and human response often lags behind infrastructural and technical progress. And this is one area where the multinational transport strategy identifies educational campaigns as being the most effective method to close the gap between these fast changes in the infrastructure and human response, right? So here it is about studying responsible driving and cycling. We won't be implementing the educational campaigns, but instead we will be demonstrating what can be done with some examples. And these are some examples which might be good candidates to target. So this first picture here, we've got, this is at the entrance to a roundabout. And most of our roundabouts now have got this green path here, which is for cyclists. But we get cars, and many of them, who stop on the cycle path, obstructing the cyclists. So this could be one of them. The other one is we do have cyclists, especially those who cycle for sports rather than commuting, who don't make use of the green infrastructure. So the authorities or researchers might be interested in, or the bicycle lobby might be interested in data on statistics. How many cyclists use these and how many cyclists don't, and why not? The picture here shows a bus that is not parked next to the curb, and it reduces the space on the carriageway and so on. We have another problem in Malta where cars turning right or into the road, they go on the other side of the road. So these are examples where we will be training models. In this case, we will be developing this use case to demonstrate technology to classify actions into exemplary and objectionable behavior. So the technology can be used to study the study of objectionable behavior on the road, and it can also be used to design and evaluate educational campaigns. So first, the user will study and see which behavior the educational campaign should target. And then after the educational campaign, the user can also evaluate how effective it was from data before and data after. And essentially, this is an offline case where we have the video audio, it is stored, passed through the AI models, and it outputs statistics and visualization. The third, our third use case is traffic conditions and anomalous events. And the intention is to run this in quasi-real time. So in this case, we will be monitoring traffic condition, flow rate, and volume of traffic. For example, here the pictures show some various levels of traffic, and automatically detect anomalous events over time. For example, abnormal traffic jams may indicate other anomalies downstream. For example, there was an accident or there is some road work going on. Stationary vehicles obstructing a junction or a carriageway. And sometimes we get service vehicles parked on the sides, which create abnormal traffic congestion. So the idea here is to execute this in quasi-real time. And it also includes low-cost AI models that are computed at the edge. And this would actually reduce the amount of data that has to be transmitted and dealt with. And some potential application for these technologies include real-time automatic traffic monitoring, systems intended to inform drivers of traffic state or anomaly, and more importantly in Marvel is raise anomaly at traffic management control rooms, where traffic managers can manually review the data and take any necessary action. And our fourth and last use case is regarding junction traffic trajectory collection. And this is focused on the requirement of long-term data analytics for long-term transport planning and evaluation. It sheds light on how and when traffic entities, such as car drivers, motorcyclists, cyclists, etc., use the infrastructure. For example, at the moment, there is a lot of interest in how cyclists use the infrastructure and how micro scooters are being used. So this is essentially, it's about gathering traffic statistics from the road network. And these are some examples that would be interesting for Malta. For example, counting the number of heavy vehicles passing through residential streets, optimizing the position of pedestrian crossings. For example, in this case here on the right, we've got an area where there is a pedestrian crossing over here, but it seems that most people cross from this part. And the authorities are interested in knowing where pedestrians prefer to cross. Another one is studying whether provisions for cyclists at complex junctions are adequate, and whether these installed provisions for cyclists are being used as intended. Technology-wise, this is about offline processing of video and data. And the user interface will allow the end user to select the data and task to do. The task would normally consist of filters made up of AI models. Potential end users will see traffic engineers, consultants, and planners, and also transport researchers engaged in academia and transport authorities who are interested in studying mobility. So technology-wise, we need the detection of entities and their trajectory. We won't be only detecting the entities here, but we will be also computing the trajectory across the camera view, which is the junction or the road segment. We need anomaly detection algorithms as well, either based on audiovisual directly or post-processing the detection of the entities and trajectories. And it also requires, of course, the output converted to descriptive statistics and visualization. That was the end of my presentation. Thank you very much.